see my files. Okay. Hello to all dears. I am Bagari, and you know I will present this lesson to you. Hello Mustafa, welcome. I'm very happy to be able to work with you in this class. I hope we have a successful course in this semester. In this course, I will study the basic concepts needed in harmonic analysis, okay? Harmonic. First, a set syllabus of this course. But promise this established, I apologize for the internet problems and the lack of classes in the previous weeks. Okay, let me write this in Google Translate. Okay, okay, Afan, and I hope classes will be held in time from now on, inshallah. And we will probably have face-to-face classes for a few weeks. Let me write again. Okay. على الأرجح سيكون لدينا فصول دراسية وجها لوجه لبعض الأسابيع. We will probably have face-to-face classes for a few weeks. Okay? But currently classes are held in person on or online. Okay? Currently classes are held in person on. Okay? Do you understand, dear students? Do you understand? Okay. Let me show the topics or syllabus of this course, harmonic analysis. We consider some topics in this course such as these: topological groups, construction the product measures, invariant means, convolution of measures, representation theory, dual groups, almost periodic functions, and amenable groups. I will try that express some basic definition and concept of this syllabus. Okay, and there are many books in these subjects such as abstract harmonic analysis written by Hewitt and Ross. This is a basic and important source and book in harmonic analysis, or other references such as this: a course in abstract harmonic analysis written by Folland, or these books for Rudin and this for Ali Prentice, or the books written by Ritter and Stigman, classical harmonic analysis and locally compact groups, and other books that you can see in this slide. We begin by this book at first, an introduction to topological groups, for the first topics of this course. Okay, written by Spivak, that I sent this source for you in WhatsApp. Okay, do you see, dear students? Let me write. لقد أرسلت لك هذا الكتاب على واتساب. My voice was up. I'm very sorry. Do you have my voice, dear students? Okay, sorry. I repeat this definition again for you. This is the definition of a topology. Let X be a set and tau is a subset of P of X. Tau is a topology on X. Whenever we have these three property, empty set and X belong to tau, for any collection or sub or element of tau, the union of these elements belong to tau, I is arbitrary. The number of this element is arbitrary, okay? And 3, for any two elements, A1 and A2, in tau, its intersection belong to tau. And I take an example. Let X equal to this set A, B, and C. And consider tau as this subset of X. Empty set A, B, and C, and X. Yes?
Sorry, doctor, we don't have any
Muhammad
picture.
Hassan, do you have any question?
Yes, doctor, we don't have the picture. We just hear your voice.
Mr. Muhammad Hassan, a picture?
Yes, doctor, I hear you. We don't have any picture. We just hear your voice.
Thank you very much.
Thank you, doctor. Uh-huh, yes, yes,
Thank
yes. Now we see.
you much.
Yes, now we have a picture.
Do you see these slides? Do you see? No? Do you see this slide? Dear students, you must. هل ترى الصبار and هل عندك صوتي and هل ترى الصبار. Yes, for sober and for voice, okay? Okay, thank you, Muhammad Hassan, thank you. I'm sorry for this problem. Okay, I repeat again. Definition that X be a set and tau is a subset of P of X. Tau is a topology on X whenever we have these three conditions. Empty set and X belong to tau. For any collection of elements in tau, the union of these elements belong to tau. For any arbitrary element, okay, and for any two element of tau such as a1 and a2, we have this intersection belong to tau. See this example. Let X equal to this set and tau equal to this set. And note that tau is a subset of P of X. All of these are sets or subsets of X, okay? Subset of X. This tau is a topology on X, and this is very easy because we see that empty set and X belong to tau, and we have the first condition and the union of any number of these elements belong to this tau again. For example, the union of these two sets equal to A, the union of this equal to whole of X, the union of these two sets equal to whole of X, and also we have this condition, the intersection of any two elements in tau is an element in tau. For example, the intersection of these two is empty set. Intersection of these two set is empty set. Intersection of these two set is B and C. So that we have these conditions too. Okay, there is no any problem. Voice and okay, thank you. You understand this definition and this example, dear students? Let me write. هل فهمت تعریف توپولوژی؟ Okay, yes or not? Okay. Thank you very much. So that for any set and for any subset of P of X, if we have these three conditions, we say that tau is a topology. As another example, consider this. For any set X, whole of P of X is a topology. Okay? P of X. Because in the definition of topology, we say that tau is a subset of P of X. Now, if we consider whole of P of X, this is a topology. And this is very easy again. Please note that P of X is the set of all subsets of X. P of X is the set of all subsets of X. So that trivially we have A is an element of P of X if and only if A is a subset of X. Okay? These two are equivalent. So that if we consider tau as this set, we have the first condition trivially because empty set and X are subsets of X, so that these two sets are belong to P of X or tau. And the union of any collection of subsets of X is a subset of X too, okay? This is very easy that. if or we can write if you consider alpha, assume that A alpha is a subset of X. Then trivially this union is a subset of X. By this definition of P of X, this is equivalent to this. If this is a collection in tau, then its union must be belong to tau, because we consider tau as whole of P of X. So that this is P of X and this is equal to this union is an element of tau or of is an element of P of X. Okay, so that we have the first or second condition in this example. Okay, these two are equivalent, and so we have this property. And for the second property, closure under finite intersection, we see that if A1 and A2 are elements in tau, tau equal to P of X, okay? So that A1 and A2 are subsets of X by this. A1 and A2 are in P of X, so that both of them are subsets of X. So that its intersection is a subset of X too. Okay? These are very, very important. Okay? If we consider any two elements, its intersection is a subset of X2. Sorry. Muhammad Hassan, do you have any question? Okay. Yes, students, do you have my voice? Okay. Do you have my voice? Okay. Do you have my voice? Okay, okay. Sorry. I said that if we consider any two subset of X, its intersection is a subset of X2, okay? But this meaning that this intersection is a subset of P of X and P of X equal to tau in this example. In this example, we consider tau as P of X, okay? So that it is very trivial that P of X is a topology on X in any set X. And also we have an extreme example too. Let X be a set, then this set, empty set, and X is a topology. And this is very trivial too, because we see all three condition holds. For example, empty set and X belong to 2. the intersection of these two sets is empty set, and the union of these two sets is full of X, so that this set is closed on their union and intersection, okay? So that this tau is a topology 2. So that we have two extreme examples, this example and this example, P of X. So we see that if tau is a topology on X, then this tau is within these two topology, MT and X and P of X. We see that both of these are topology. Any topology on X must be within these two topologies. So that this topology is the smallest topology on X. Smallest. Because any topology on X is contained this topology. Or this topology is a subset of any topology on X. This topology is a subset of any topology on X. This topology is called indiscrete topology. Okay? Indiscrete topology. And P of X is greatest topology on X, because any topology on X is contained in P of X. This is discrete topology and this is indiscrete topology. Okay? That we see this example in example 2.2. So equal to P of X, so is called discrete topology. Here P of X is the notation for the power set of X. Power set is meaning the set of all subsets of X. The set of all subsets of X. And tau equal to empty set and X, tau is called in discrete topology. So this is indiscrete and discrete. Okay? And any topology on X must be within indiscrete and discrete topology. And we have this note that this is very easy too. Any topology tau, such as tau, okay, is closed on their finite intersection, not two elements, closed on their finite. And you see that in this definition. For this condition, we say tau is this property say that closure on their finite intersection, or tau is closed on their finite intersection, not two, okay? Finite intersection. And this is very easy, and we can prove this by induction. By induction. Okay? Because if tau is a topology, we know that the intersection of any two elements of tau is in tau. No, for any, if we consider for any n in natural numbers, this intersection belongs to tau, then in intersection of a1 up to the an equal to this. And by induction assumption, this is an element of tau, and this is an element of tau, and this intersection must be belong to tau because tau is a topology, and topology is closed under two elements. So that these two conditions are equivalent for each a1 and a2 into we have this intersection belong to tau, or this condition for each n element of tau, this intersection belong to tau. Okay, these two are equivalent. If we consider this condition, you can consider n equal to 2, a1 and a2, okay? So that we have this implication, and for this you can consider an induction that we say for u, and we have an definition again. Let x be a set and let tau1 and tau2 be topologies on x. We have two topologies, okay, on x. If tau1 is a subset of tau2, then we say that tau1 is coarser than T2. Tau1 is coarser than T2. And let this why we don't change this relation. And in the same relation, we say that tau1 is coarser than T2 and T2 is thinner than T1. T2 is thinner than T1, okay? I write this for your understanding, but it is a question that when T2 is a subset of T1, why this is coarser and this is thinner? Okay, let's see this definition again. If tau1 is a subset of T2, then we say that T1 is coarser than T2. Not T2 is coarser than T1. Is coarser, and this is thinner than. Why this is thinner? Because this probably have smaller smaller objects by this property. Please note that by this property, when two have more elements, these finer elements are more into two. Okay? So that we see that if this is T2, T1 must be have more elements such as this yellow element or object. Okay? Or for example, maybe you consider T2 by these elements if this is a subset of, for example, T1. T1 have all of these elements. Okay? And in additional have other elements too. Okay? So that this is thinner than this. This is coarser than T21. Okay? And we have this definition. Euclidean topology on Rn. The elements of the Euclidean topology on Rn R is the real numbers. Okay? And Rn equal to the product of real numbers n times. Okay? Okay. The Euclidean topology on Rn are unions of open balls in Rn. So that in the case x equal to R, so is this topology the union of open intervals such as this. Okay, all of these are open intervals if we consider arbitrary union of open intervals. This collection is a topology on R. For example, for this topology, we see that all of these belong to tau. Okay, all of these must belong to tau. or for example this is an element of two, or any union, any arbitrary union of open intervals. No, it is very trivial that these two have topology properties. For example, empty set is an element of two and whole of R is an element of two. Okay? Because empty set equal to this, for example. We can consider empty set equal to this union if we consider index set equal to empty set. You know that the union of set that the index set is empty set equal to empty set. Okay? Or you can consider this set such as two one. Is it equal to empty set? Because this is equal to the set of all x such that x is greater than 2 and less than 1, and this is empty set. Okay? Because in intervals this must be less than this. But if we can consider intervals ordinary, okay, then consider intervals ordinary. This empty set must belong to 2, and for this condition we see that R equal to, for example, this union, okay, and from 1 up to the infinite. Okay, minus 1 1, minus 2 2, minus 3 3, and up to the end. This union equal to R, so that R can be write as this and empty set can be write as this, so that we have the first property of topology, and trivially these two have the second property of topology, because if we consider any element of 2, Let me write for you. If you consider an arbitrary collection in tau, okay? Then for each alpha, a alpha is an element of tau, so that a alpha equal to the union of intervals such as this, such as this. A alpha I, B alpha I متعلقة ب I belong to I alpha. Each alpha must be have this form, okay? So that we can write A alpha equal to this. Now, please note that the union of this A alpha equal to the union of these unions, okay? I belong to A alpha and alpha belong to, and these unions have these forms again. This is an union of open intervals, so that this is belong to tau. Please note that for any collection in tau, this union is an element of tau. So we have the second condition of definition of topology, and similarly for two elements such as A alpha equal to this union, and A beta equal to this, okay? For beta, for example, J belong to A2, then this intersection equal to this intersection, okay? A alpha A, B alpha A I intersection this union beta I, B beta or J, I or J. This I must be belong to I1, and this J must be belong to I2. Please note that we have this and this and this. We can write by another color this intersection, okay? This intersection equal to this intersection. This intersection. And this is equal to union. I belong to A1, J belong to A2, and A, B, intersection by A and B, this and this, okay? This intersection. And this is an open interval or empty set. If this is empty set, this is not important for this union. And other case, this is an open interval, so that this is a set by this form again. This is a set by this form, so that this is an element of tau. Okay? For any two element of tau, its intersection is an element of tau, and we have the search condition for topology 2. I check this two property for Euclidean topology, okay? Euclidean topology is this in R and this in Rn. Okay, so that Euclidean topology is unions of open balls, unions of open balls or open intervals, open balls or open intervals, okay? This set is closed under arbitrary union and closed under finite intersection. Okay. I think it is enough for this session, and we can continue in the next session, okay? Yes, tomorrow, Mr. Abdul Jabbar, we can continue in tomorrow at 5 o'clock. Please write this example for itself. Please write again for yourself and check these three conditions. Close under arbitrary union, close under finite intersection. Okay? Thank you very much. Thank you for your attention, and see you later.